This video will explain few loss functions for classification tasks. Before going to loss functions, I wanna define few notations throughout this video. Okay, when we design a neural network deep learning algorithm for classification task, we usually have two last layers, such that one layer for score for each class and one layer for softmax, which represent kind of probability your input belong to a specific classes. So basically, the dimension of score vector and softmax vector is equal to the number of classes. So let's say the capital K is the number of classes we have to consider. So for the score vector, I will use S1 xi, S2 xi up to S capital K xi to denote score of each class. Here the number indicate the class index. And I will use the notation S xi to denote the vector consists of its score values. Likewise, I want to define a softmax vector using g function. So here gxi is the softmax vector for the input xi, which consists of capital K number of elements. Here each g1 xi, g2 xi up to g capital K xi values present some probability your given input xi belong to class. So here gk xi means the probability your operable yi is equal to the class index k when the input is xi. Okay, so this is the notation what I want to use. So because the softmax vector is a kind of probability vector, all elements of softmax vector are positive, and sum of softmax vector is equal to 1. Okay, so the first loss function for classification task is negative log likelihood. Okay, here the loss value is just minus log gyi, the log likelihood of softmax value for the ground truth class yi of given input xi. This is log likelihood value. And if we correctly classify the output I, then our softmax value gyi should be close to 1. So that's why minimizing negative log likelihood value can train your network so that your output can correctly classify your output yi. Okay, so we usually sum up the negative log likelihood value from first image to or first data to the last data when there are n number of data point. Okay, we also use cross entropy, which is a very popular metric, to measure the distance between your softmax output and the target output. So in this case, the target output yi also a vector and a probability vector. So all elements of yi is non-negative, and the sum of elements of yi have to be equal to 1. Okay, so there is some y, I, and we have some score value. And let's say, and softmax value. So let's say the log g xi is the vector consists of log g1 xi to log g capital K xi. Then the cross entropy value is basically inner product between the target output vector yi and log g xi, thus log softmax vector. Essentially, cross entropy loss function is more general loss function compared to negative log likelihood function value. For instance, when you have this one hot vector for the target yi, then basically cross entropy exactly the same with the negative log likelihood function. Okay, so cross entropy is more general sense of loss function. Right. And sometimes we have to use Kullback labeler divergence or KL divergence, especially when you study variational autoencoder or generative adversarial network. You will meet KL divergence very often. Okay. Then what is KL divergence? This is very simple. Again, yi is a vector, a probability vector. All elements are positive and sum of elements equal to 1. And we have log g xi vector. Okay, the KL divergence is the inner product between yi and log yi vector minus yi log g xi. So this is kind of sum of minus entropy of y plus cross entropy. Okay, so when we cannot control the yi vector, then KL divergence essentially the same with cross entropy because this is a constant. But when we can control the yi vector as well, then KL divergence has some meaning, some different meaning compared to cross entropy. So that's why in generative adversarial network literatures, we use KL divergence rather than cross entropy, because in that case we can control yi vector as well. Anyway, KL divergence is very famous divergence metric that can assess the difference between the target distribution and your current generated distribution. Your target distribution vector and your current estimation vector. Okay. Right. On another loss function for classification task is hinge loss. Hinge loss has very different property compared to all three previous loss functions. So here the loss function is max of 0 and score value of Sj xi minus score value of the true label yi xi plus 1, and we want to sum over all index I, which is not equal to the true label yi. Sorry. So this is j. Sorry. Okay. So essentially, when you minimize the hinge loss, you want to decrease, you will decrease the score value of all other and all entries except the entry having the true output. Okay, and then in the end, the score vector will have very high value at the true label and very tiny or small value for all the other entries, which is kind of desired score vector, and we can expect very accurate prediction or classification with hinge loss. Okay. So before deep learning era, support vector machine usually use hinge loss, but in deep learning era, we actually very rarely use hinge loss. We usually use cross entropy or negative log likelihood or KL divergence.